Okay, hi. I want to thank the organizers for a great conference. It looks amazing. Yeah, so good job. Uh, um, yeah, so today I want to talk to you about unimodular triangulations of matroid polytopes, and this is joint work with Spencer Bachman from the University of Vermont. Okay. So we've heard about matroids before. So I'll just quickly go over the definition. So I'm going to, for the purpose of this talk, a matroid is a collection of subsets, which we call bases of, we'll just say, of the integers 1 through n, satisfying a property called basis exchange. This says that for any two bases, A and B, you can choose some element in one of them, and then there always exists some element to the other, such that you can delete one and add the other and get another basis. Okay, and sort of the prototypical example is that if you have some finite set of vectors which span a vector space, you can take the collection of all vector space bases among these vectors, and that will give you the vectors of a matroid. The bases of a matroid. Okay. So I gave you a definition, but that definition is not important. So I mean, what I really want to think about as a matroid is using the following theorem due to Edmonds, and then later independently Gelfand, Gorski, McPherson, Serganova, which is that if you have a collection of subsets of bracket n, then this collection is a matroid if and only if you take the polytope, what you get by taking the convex hull of all the convex hull of all the indicator vectors of these bases. So you take a basis and you sum all the standard basis vectors corresponding to that basis. And then this will give you a polytope, and it's a matroid if and only if this polytope has every edge parallel to ei minus ej for some I and j. Okay, and this is called the matroid polytope. Okay, so this has been seen in some other talks, but I'm not going to assume everybody's seen every talk. Okay. So this is an example you always see. If you take the uniform matroid on 4 elements of rank 2, you take all 2 element subsets of bracket 4. This gives you a polytope in R4, but it's actually 3-dimensional, and it ends up being an octahedron. Looks like this. And if you go to matroid talks, you'll definitely see this, because this is the only example that you can really draw. So. Everything else is higher dimensional. Okay, so in just some other pictures of matroid polytopes, you can take if you just take the top half of the octahedron, you get a square pyramid. It's a matroid polytope, and you can take like a square or a triangle, which are faces of this matroid polytope. So if you take any matroid polytope and you take a face, that will also be a matroid polytope, simply because it satisfies the edge condition. Okay, so that's the first part of the title, matroid polytopes. The second part is unimodular triangulation, so I'm going to define these. So now we want to talk about lattice polytopes. A unimodular triangulation is defined to be some lattice triangulation where every simplex has volume 1 over the dimension factorial. Okay, so here I've drawn some polygon in R2, and then in red I've drawn a unimodular triangulation of this polygon. So every triangle in this triangulation has area 1/2, and so this is a unimodular triangulation. Okay, so you can prove that every lattice polygon has a unimodular triangulation, and this is essentially due to the fact that you can very easily describe any simplices in R2, and you can use a Pick's theorem to get the area. However, when you go to higher dimensions, becomes a non-trivial question, and in fact, lattice polytopes do not always have to have a unimodular triangulation. So, for example, you can take the following simplex, I forgot a coordinate there, but it should be 0, 0, 0, 1, 0, 0, 0, 1, 0, and then 0, 0, some large number, say 9. And this is and you take the simplex, and a property that the simplex has is that the only lattice points it has are its vertices. Okay, so in fact has no non-trivial triangulations. Okay, so it has no non-trivial triangulation. So if you want to triangulate, you can only take itself, but itself you can calculate the volume is not 1/6. What did I write? Oh yes, 119. Yes, thanks. Yeah, sorry. It should be yeah, those should be ones. Thank you. Okay. Okay. And then unimodular triangulations, they sort of appear in various contexts when you so lattice polytopes have connections to various areas of mathematics, and oftentimes having unimodular triangulation has some consequence in that area. So just to briefly give some buzzwords without explaining anything, Earhart theory, Grosvenor bases, and resolutions of singularities. All right. Okay, I mean, I could if you're interested in one of these, I could talk to you later. But in general, it's hard to construct unimodular triangulations or prove their existence. So, if you give me just some random polytope, I probably won't know if it has a unimodular triangulation or not. And even if you tell me it has one, I probably won't be able to construct it. So yeah, so just to demonstrate how tricky this can be, it's an open question whether or not any three-dimensional lattice parallel pipette has a unimodular triangulation. So just a parallel pipette, like a rectangular prism, do these always have unimodular triangulations? We don't know. Okay. Okay. So all right. So in general, we don't know if things have unimodular triangulations, but for specific classes of polytopes, you can ask, are there maybe systematic ways to construct unimodular triangulations? And one such class of polytopes that you can do this for are things called alcoved polytopes. So you saw these in Carolina's talk. And these are polytopes whose facet defining equations are of the form xi plus xi plus 1 plus xi plus 2 and so forth up to some other. So you take a consecutive sum of coordinates and you just set that equal to something. Okay. Alternatively, after a change of coordinates, you can say that the facets are defined by things like yi minus yj equals something or yi equals something. But that's often useful, but it's equivalent. Alcoved polytopes, it was mentioned that these can always be unimodularly triangulated, so I'll explain how you do this, and this is through a process called dicing. So what you do is you sort of take all the hyperplanes of the form, you take a sum of coordinates equal to some variable, you just take all those hyperplanes, and you dice your space using these. And then so you just put them all in. This will actually cut up your space into simplices, and all these simplices will be unimodular. Okay. Just sort of a picture of this in R2. I've taken, so this is an alcoved triangle defined by the hyperplanes x equals 0, y equals 0, x plus y equals 3. And then I dice it by hyperplanes that are parallel to these, and this gives me a unimodular triangulation. Okay. And then matroids whose polytopes are alcoved, these are called positroids, as we saw. And then so positroid polytopes therefore have unimodular triangulations. Okay, so this is something that's very special to this specific class of hyperplanes. In general, if you sort of do this dicing operation, you won't even get a triangulation. Okay, so now I can get to the main theorem of the talk, which is that any matroid polytope So we saw that positroids have unimodular triangulations, but in fact, all matroid polytopes have regular unimodular triangulations. And I'll get to what regular means later. You can extend this theorem to just a general integral generalized permutahedra. This includes up to affine equivalence, matroid independence polytopes. And this was conjectured by Hawes in his 2009 thesis. Okay. Questions so far? Okay, so I think before this, it was not really clear whether or not this was true or not. At least, for a while I thought this probably was not true, but it turned out to be. So I guess it's sort of hard to know when things will have unimodular triangulations. Okay, but when we were working on this problem, we were actually not specifically trying to find unimodular triangulations. We were working on another problem. So let me explain what this other problem is. So let's say given some matroid defined by its bases b on bracket n, I'm going to define its toric ideal to be the kernel of the following map. So I take the polynomial ring. The field doesn't matter, but I just take the polynomial ring where the variables are indexed by bases of the matroid. And I send that to the polynomial ring where the variables are indexed by the elements of the ground set. And this map is I just send a basis to the product of its elements. Okay, so this is also the toric ideal of the matroid polytope for this matroid. And conjecture by White is that the toric ideal of a matroid is always quadratically generated. So it'll end up being elements of the form xa times xb minus xa prime times xb prime. Okay. So this has certain combinatorial interpretations. One way you can explain this combinatorially is the following. Let's say I have a multi-set of bases of my matroid, and then I have another multi-set of bases of the matroid, and these two multi-sets have the same multi-set union. So if an element appears 3 times in one multi-set, it should appear 3 times in the other multi-set. And what this is saying is I can go from one of these multisets to the other by doing the following operation. I take 2 bases in one of my multisets, and then I swap some of their elements. And then that's one operation. I keep doing these operations, and then if I can do, what the conjecture is saying is I can always do some sequence of operations to get the other multiset. Okay. Okay, so I called that White's conjecture, but actually he conjectured several things. So I put some of them here. So the weakest form is that the toric ideal is quadratically generated, but another thing that he conjectured is that the generating set for this ideal is elements of the following form. xa times xb minus basically swapping 2 elements between these 2 bases. And this is what's called a symmetric exchange. You have 2 bases, and it's always possible to take one element of one and another element of the other and just swap them and get 2 new bases. And so he conjectured that you can that this toric ideal is generated actually by these elements. Okay, so this is from the 70s. And then later, in 2002, Herzog and Hebe were sort of looking at this conjecture in the view of polymatroids, and they actually made some other conjectures. I guess because they're commutative algebraists, and so they sort of say they want to look at. So it was natural of them to think of this. So stronger than this ideal being quadratically generated is that this quotient has a property called a causal. So I'm not going to go into what that is, but it's a sort of a stronger property than this ideal being quadratically generated. And then stronger than this is it's a statement that this ideal has a quadratic Grobner basis. Okay, so I'm not really going to explain what these are, but I'm sure people in this audience would be familiar. Many people in this audience would be familiar with this. Okay, and then if you really want to, you can make an even stronger conjecture, which is that these elements here form a quadratic Grobner basis for the ideal, which was done by Hawes 2009. It's not proven, but conjectured. Right, so that's sort of this. So sort of collectively, these are often known in the community as White's conjecture, even though I guess yeah. Okay, and this is sort of the conjecture that we were trying to tackle. I think, well, we were sort of looking at both sides and sort of seeing what we could do. And at least from a geometric standpoint, since sort of my specialty is sort of polytopes and things, so we're mainly sort of interested in this one here, that the ideal has a quadratic Grobner basis. That's because it's due to this correspondence by Sturmfels, which is that well, there's a correspondence between Grobner bases and convex geometry, and in this case, what translates to is that this ideal has a quadratic Grobner basis if and only if the matroid polytope has a unimodular, regular, and flag triangulation. Okay, so now I'll define what all these terms mean. So we saw what unimodular means, and what regular means is that it's induced by some real valued functions on its vertices. So what that means is I can sort of assign numbers to all its vertices, and then if I lift this polytope according to these numbers, and then so I get these folds, and then if I sort of project back down and remembering where the folds are, I get some triangulation, and that's what a regular subdivision or a regular triangulation would be. And then this property flag says that every click in the one skeleton of the triangulation is a one skeleton of the cell of a triangulation. Okay, so I tried to draw these pictures. They worked better in my head than they ended up. So you probably don't know what's going on. But okay, so I have a bipyramid. And I've triangulated in two ways. So in one way, I've triangulated it into two simplices like this, one on top of the other. And in the other, this is a triangulation with three simplices. I've sort of drawn this line segment down the middle, and there's three simplices that all share this line segment. So this is a flag triangulation, but this is not a flag triangulation because if you take this sort of triangle in the middle, this is a click in the one skeleton, but it's not simplex in that triangle is not a simplex in the triangulations. This would be a non-flag triangulation. Okay, so if you have a triangulation that satisfies all three of these properties, unimodular, regular, and flag triangulation, then that will imply that the ideal has a quadratic Grobner basis. Okay, so I want to mention. Okay, so I want to mention now. So we as I said in the theorem, we were able to prove that we were able to get two of these, regular and unimodular. So I want to mention that that our construction, it gives us a way to actually compute these triangulations, and that's actually not just one triangulation, it's many, many triangulations. So what we did was with Matt Larson, Samuel Payne, we used our construction and to try to computationally search for some regular modular triangulations, which were also flag. But we searched for a while, but we were unable to find any for example, for the Fano matroid. Right. So, and there was also other computational experiments done for the Fano matroid. I think one team had a program run for like a year, and they were not unable to find something. So, maybe I think that is evidence against. So, just saying. Okay. So, I'm almost out of time, but I want to sketch the proof a little bit. So the idea of this proof is to basically take advantage of one of the only properties we know about matroid that we can do for any matroid, which is deletion and contraction. So what we're going to do is we're going to partition the vertices of the matroid polytope into those which have a 0 as the first coordinate and those which have a 1 as the first coordinate. And we're going to call these polytopes P0 and P1. So if you're familiar with matroids, this corresponds to the deletion of the first element and the contraction of the first element. Okay, so P0 and P1 are matroid polytopes being faces. So by induction, we have unimodular triangulations of them. We have regular unimodular triangulations of them, so that we know that there exist functions f0 and f1 which induce unimodular triangulations of these polytopes. Okay, and now what we want to do is we're going to sort of triangulate these polytopes using these functions, and then we're going to tilt one of the pieces by a little bit. Okay, so what I'm going to do, or sorry, not by a little bit, by a lot. So what we're going to do is we're going to take some generic linear functional L. I don't have explicitly what it is, but we know it exists because we know the things that can't be, and those are and that we know there's not a lot of those. So we take some generic linear functional, and we consider this function f of x1 through xn equals, so if you're on the bottom piece, you just take epsilon times your function f0 you got by induction. If you're on the top piece, you take L plus epsilon times f1. And then here, epsilon needs to be sufficiently small. And the claim is that this function will induce unimodular triangulation. Okay, so quickly, what is the idea behind this? So so when you do this, what you'll get is if you start just by doing this L, what you'll get is some subdivision that will kind of look like all the cells will be of the form where you take a face of this top polytope and a face of the bottom polytope, and you take the convex hull of those. And then when you sort of add in this epsilon times f0, f1, well, you'll further refine this subdivision. Okay. And sort of the key observation is if you take this f0 and f1 and you sort of look at the following vector spaces, you take the span of all differences of basically all vectors contained inside of this face. These have this property it's called several things in the literature, but is purity or total unimodularity. That if you take the lattice span by one of them and the lattice span by the other, then that equals the lattice you get if you combine these combine these spaces and combine these spaces. Okay, so real quickly what that looks like. So here I have two spaces, x and y, which have this property. If I take the last points in here and take the last points in here, they generate the entire lattice. Whereas these two vector subspaces don't have this property. If I take this the last here and the last here, they span this lattice, which is not the entire lattice. The fact that these two spaces satisfy its property is a special property of matroids. So this is where we need to use the fact that we're in a matroid. And it basically comes down to the fact that the AN root system has this total unimodularity property. This is sort of special to the AN root system. Okay, and then so then there's just you can show that basically using this that every simplex you get from this function is unimodular. Okay, so I'm out of time, but I think that's it anyway. So thank you, everybody.
Okay, thank you. I see many questions.
Thanks for the talk. So you said, for example, the phonomatroid is one of the ones where you can't get all three properties to hold in general.
Yeah, we don't know. We weren't able to.
So do you have examples of, say, stuff that's real representable? So Phano is only representable over characteristic 2 and not over the reals, for example, right?
Right. Yeah, so I don't think we can do, like, for let's say K5. So,
Okay. Thanks.
yeah.
This correspondence of Sturmfels is either direction constructive, like if you construct a Grosvenor basis.
Yeah, it's pretty explicit.
Okay, thanks.
So were you able to check any of the other versions of the conjecture for the Fano matroid and see whether it does or doesn't satisfy the things?
Yeah, so I think it's actually pretty easy in those cases. Let's see. Yeah, so I think this one, it's been shown for all matroids up to a certain rank, and that rank includes the Fano matroid. So, yeah.
Oh, yeah. Go ahead.
I have a question. So you have a triangulation. Do you have any combinatorial interpretation for the simplices of the triangulation in terms of the matroid itself?
Yeah, so that's a good question. I would say no. I mean, I guess it depends on what your definition of a combinatorial interpretation is. I mean, I can give you like a geometric, how you could come up with like a geometric description of them, but if you want me to actually like tell you, like actually like give you a list of them somehow, or like have a computer give you a list of them, I don't really know how you would do that. Yeah, so I mean, part of the proof is that you sort of just do this, do this generic lifting, and then the magic of the theory of subdivisions does everything for you. So that's sort of if you don't want to get into the weeds, that's a bit harder.
So, yeah, the subdivision you construct, I mean, it corresponds to a certain initial monomial ideal of the toric ideal, right?
Okay.
And I mean, obviously it's not quadratic in general, but so have you looked at these ideals? I mean, maybe you have some kind of bound on the degree they're generated in. I mean, well, hypothetically.
Yeah, I don't know. So I mean, if I remember correctly, it should be that the unimodularity will say that the monomials are square free.
Yes.
I mean, that's all I know, so I haven't really looked into.
Okay.
Yeah, specifically.
Thanks.
Now it's working. In the case of pository polytopes, the triangulation of the hypersimplex, which is the pository polytope for the uniform matroid, has a nice property that refines all positoid subdivisions of the hypersimplex in pository polytopes. Do you have something similar, that there is a unimodular triangulations in such that refines the matroid subdivisions that are regulated by the Dressian?
Yeah, it's a good question. I would assume no. Yeah, so I mean, okay, so if you, I would assume no, but I haven't thought about it.
For the sake of time, if you have more questions, please ask him later on. So let's thank Gaku again.